Welcome you all to this course on defects in materials. In the last class, we covered about the how strains are introduced, various components of the strain, okay, and shear strain as well as pure strain, okay. All of them are present. Then how we can transform that into a form where only the principal strains are either pure shear or pure strain, okay, or a pure shear. That way how we can transform them, okay. And then another aspects also which we considered is that whenever we strain a lattice, especially when we shear a sample, it's possible that the external form of displacement which we give, okay, apparently could be that pure shear component may be full deformation which has been given, need not be pure shear, it could be partly a shear plus a rotation, okay. How to separate these? These are all the aspects which we have covered, okay. What will be the consequence of trying to apply a shear on a material, the strain a material? Suppose we take a material, okay, pull it in these directions, give rise to an elongation. Assume that at some particular plane, arbitrarily we draw a plane, okay. Assume that there are atoms on either side of it, okay, across an atom. Then when we try to pull that sample apart, the body will exert, okay, develop an internal stress which will oppose the external stress which we are, force which we are applying on it. So that means that now the atoms on either side of, or the separation between them is away from the equilibrium separation. So they will try to come back. So there will be a force which is acting from here on this side and a force acting from here on this side on that plane. Finally, when the stresses are equal, it is in that equilibrium position, okay, static equilibrium. Forces are always going to be there. We assume that, okay, on an atomic strict scale, that is looking at distances of the order of atomic separation, if the force doesn't vary, okay, that's one assumption which we make. Then, and if it is constant, then we can represent this in terms of what we call it as the force per unit area. That's what we call it as a stress. Sigma equals limit, that is, if we assume that the force is being applied in some particular direction, okay, then what we know is essentially across some area of the sample over which this force is being applied, okay, the force, okay, as the area becomes tends to 0, what is going to be the force? That is called as the stress. This is how the stress is being defined, okay. Is this clear? Okay. This generally when we try to wanted to measure a force is a vector, okay, it's always applied in a specific direction. Normally when we do experiments, what do we apply? What we know is some load which is being applied. We know what is the area over which this load is being applied. From that we can calculate that stress, correct, right? That is the only way we can do that, and that stress per unit area can be called as equivalent to a force, right? Force cannot be directly, because what we do is experimental part of it is only the load which is being applied. The load will be applied over any area, okay. From that we have to calculate the force, correct. How do we go about doing it? The divided by the area, we get that, correct, and multiply by that area, that force will come into the picture.
From load to
yeah, but first should know what is the area to which we have applied it. Yeah, yeah, that is what is stress? Stress is force per unit area, okay. Yeah. That's the best way in which we can calculate the force. Okay. Now, if you apply force on any surface of the sample, small area, if a force is applied in some direction across an area, this is delta A if we consider it. Okay. This force can have, we can divide it into two components. One, normal to F, which is called as Fn. One in the direction, in the plane, okay, which we call it as Fs. Okay, we can call it. Okay. So the force can be separated into one in the normal to the plane and one in that plane. Okay. If we choose a coordinate system, and then with respect to that coordinate system, this can be further divided into two more components in the direction of, suppose x and y are lying on this coordinate system, x axis and y axis. We can further separate it into. So essentially on any surface, if you consider this surface, now we have three forces which are going to be there, or three stresses we have to consider it. One is a stress which is normal to the surface, another is two stresses which are lying on the plane, correct? And since the coordinate system which we are choosing, it is x, y and z, okay, that a Cartesian coordinate which we choose, okay, any force which is being applied in a particular direction, we can split it into components which are lying along component of this force on all these surfaces. So essentially what we will have is 9 components are going to be there total, correct? That is, if that is at this point when we are trying to measure the the net force which is applying, which is being applied, okay, that can be separated into, okay, components along 3 surfaces passing through that plane which are perpendicular to each other. Okay. Those 3 surfaces, when we consider, it is nothing but equivalent to considering a Cartesian coordinate system and defining the stresses, correct? That is what essentially is being shown in this slide if you try to look at it. Okay. In this, there are 2 notations in which the coordinates are also being represented, one using 1, 2, 3, okay, to represent the x, y and z coordinates, okay, otherwise also writing them as x, y and z. So on the positive faces is where these stresses are being shown, sigma 1, 1, sigma 1, that is sigma 1, 1 is the stress, okay, which is normal to x surface, okay, and similarly sigma 1, 2 or shear stress, the tau xy if we write it is, that is, this is applied in the y direction but on the surface x, okay. But how this surface is being defined? Now normally being defined with respect to the outward surface normal, okay. If you look at for these surfaces, the outward normal is always in the positive direction, right, okay. And so this is, so that is how we define whether it's going to be a positive or a negative value. That's being decided by the direction in which the load is being applied and the outward normal together. That defines the stress is positive or negative. That's the way. And one should be very careful that the symbols which are being used, the directions, the magnitude of the direction which we use here, it appears they are equal, correct? We should not be fooled by that, because these values could be, it's only arbitrarily it is being shown. It can have values which can be quite different depending upon the components of the force in those directions, okay. Similar to Cartesian coordinates, we can use cylindrical coordinates also. But in many cases, especially when we are looking at defects like dislocations, the Cartesian coordinate, instead of Cartesian coordinate, one can use the cylindrical coordinate, because most of the time the dislocation is taken to be, the line direction of the dislocation to be lying along the z axis, okay? And most of the displacements which are taking place, which give rise to stresses, are in the xy plane, where we can define that in terms of cylindrical coordinate itself, okay? And another aspect which one has to be very careful about it is that I have taken from two books how these stresses are defined. This one has to be very careful about it, because different books follow different notation, okay? In this particular one, the first letter represents the direction of the stress, okay? The second letter essentially is representing the plane normal, that tells us which is the plane in which it is being done. So here if you look at it, the direction in which it is being applied, sigma, okay, its y first represents it's in the y direction. You look here in the next diagram, if you look at it here, with respect to a coordinate system which is chosen, this is the y phase, okay, on which this is the y normal, which is the first letter, and x represents the direction in which it is being applied, okay. The first one is, no, x represents the direction in which the stress is applied, sigma x, and here sigma y is the y direction it is being applied. When sigma first letter z is in the z direction, it is being applied. And the second suffix represents what is the plane normal, that is Kahneman, because it is applied on this surface x. Here it has just changed, okay. Different books follow different notations, so one should first see that what is the notation which is being followed, okay, and one should use consistently one particular notation, okay. And because of this, quite often we find that some signs will change during calculations, and one should not be fooled by looking at this information that one book has given something else, other book has given an exactly opposite. That is not the case, because always all the magnitudes, okay, the value, not only the magnitudes, the direction, whether it's a positive or negative, because this can make a lot of difference. Suppose you calculate some value on the basis of the sigma x which is given. If you don't follow a consistent value, for stress we use one notation, strain you use another notation, then we will have a lot of problem between attractive and repulsive forces. A lot of confusion will come. If that should not happen, we should always follow one notation only, okay. And we should know what is the notation with which these stresses and strains are described. So far what we have defined is 9 components, especially the shear stresses when they are being sigma xy, which is shown in this direction, which is being applied in this direction, and sigma xy, which is being applied in this direction. If you look at it, if their magnitudes are not the same, there can be a net moment and there can be a rotation which it can come. Normally, in this case, when the stresses are small, the body is in equilibrium, okay, it's static equilibrium, so the moment has to be 0, because of which sigma xy will be equal to sigma yx, or this we can write it as a generalized form, sigma ij equals sigma ji. So that means that we will have 6 components of the stresses are going to be. In the previous figure, we have defined the stresses with respect to surface which are perpendicular to either x, y or z directions. This is how all the components are defined. Now suppose we wanted to find out stress along, that is the force which is being applied arbitrarily along any particular plane. That is, plane could be in any plane, it need not be along x, y and z, okay. What is the information which we have? as far as we know, is that what is the force which is going, the stresses which are acting on all the specific planes, okay, x, y and z surfaces, that information is available. If that information is available, can we find out the force acting in any particular direction on any plane? That is the whole issue is that. Okay. That means that suppose I assume that there is a force which P is acting on this plane. That is okay. In an arbitrary direction P. What we want to know, what is the magnitude of P? Okay. The P can have components, that's been, since P is a vector, it can have component P1, Px, Py, Pz in the x, y and z direction, correct? Okay. Now that means this is the component of the force in the x, y and z directions. If we get the component of this one in terms of forces which are acting on the x surface, y surface and z surface, okay, then we can get complete information about all the forces. Then the complete information, the force acting on any direction across this plane ABC, we can get it, correct? So for which what we have done is that if the plane normal is defined by, okay, a vector, and that makes Lm and N are the direction cosines of that plane normal with respect to x, y and z axis, okay. If we have got that information, this is a tetrahedron, correct? In this tetrahedron, this is the plane which is perpendicular to y is AOC, correct? That is the triangle, the area on which the stress is acting, and BOC is the area of the triangle over which, okay, the x direction force acting, and AOB is the plane over which, okay, the surface over which these stresses are acting in the z direction, okay. So if we have this information, okay, what is going to be the force if he is acting in each of this direction, okay. Suppose the component is Px, okay, what is going to be the what is G? Essentially I represent it as the area of this, okay, with respect to okay, the G into Px is the area over which the component of the force is going to be there, correct, and this is acting on this Px. We can find out to be, suppose with respect to x direction we wanted to find out, okay, the force which is acting in this sigma xx, correct, normal to this surface. In the same direction, if we look at it, sigma yx will be the force which is acting in that direction, okay. Then sigma zx is the force which is going to act on that surface in that same direction. So if you take the total sum total of those forces, okay, we get the component Px, correct. That is what essentially is being given by this formula. So this way, using this diagram, we can find out the forces which are the components of the forces in the x, y and z direction. If we know that just by using the vector notation, then immediately we can find out the direction in which the force is going to be present on the sample, on the surface ABC which we have considered. This same force which is being applied on this surface now, we can find out the component of it, which is one normal to the surface and another one which is in that plane, okay. Normal to the surface is the one which gives the tensile or the compressive stress. Okay. The stress which is lying on the plane gives the shear stresses. Okay. So these are all the expressions which are being given for how to find out these stresses. So what essentially has been done, this equation itself here, when G is going to be there, if you remove from this expression G, then this becomes Px equals sigma xs into L Zx into N, okay, where sigma xx is the stress normal to the x. This is the sigma yx is the stress which is acting on the y surface but in the direction of this one. So if we multiply it by the area, we are going to get the force. Okay. So here sigma Zx is essentially on the Z surface, but the force which is being applied in the x direction. So we are taking the sum total of it. This itself can be written in the form of Pa equals sigma Ji into, we can write it as Lj, right. This is a Einstein summation notation which we have learned earlier. Okay. Another aspect which we have to see it is that here we have calculated the components of the force, directions of the surfaces, the stresses which are acting and the phases which are parallel to x, y and z axis. This is with respect to a coordinate system which we have chosen. We can choose another coordinate system which 3 other surfaces, okay. With respect to a plane normal, if we take it, they may be making some angle with respect to the world coordinate system, like what we have learned earlier in the case of coordinate transformation. In such a case, we can find out what is going to be the stresses along different directions with respect to that coordinate system in terms of the world coordinate system, and that will be given by this formula. Right. So this one has learned. This way we can find out with respect to a new coordinate system. This will this sort of transformation we will require quite often, because the dislocations, when we wanted to calculate stresses and strains around dislocation, we define them with respect to a coordinates axis which is with respect to a dislocation, okay. But that axis does not match, is not parallel to the crystallographic axis which we choose, okay, to describe the atom positions in the unit cell, okay. Is it clear? So this way we can represent the different components of the stress and strain. What we have written this equation is nothing but a force balance equation, okay. That is, when we write this expression with respect to G, this is essentially a force which is being balanced. This one, yeah, here what we are trying to calculate, if you wanted to calculate the shear stress, okay, if we know the normal stress, so how do we calculate this stress which we have done? If we wanted to find out the normal stress, we know the components of Px, Py and Pz, okay. In the normal direction we have to find out, normal to this plane, then we will get sigma n, okay. That is why I put Pa into Li, okay. That is Li is the it represents the direction cosines which the different components, that is Px, Py, Pz, make with respect to the plane normal. Okay. So then we can find out the component of the x, y and z, Px, Py, Pz in the plane normal direction. Okay. When we add them together, we get the normal stress, correct? That is essentially what it's being written. The toe is that if we know the stress which is acting or the force which is acting in the direction of P, that we have the total one, okay, and that magnitude if you take it, this is nothing but constructing a using the Pythagoras theorem, we can find out sigma n, we know that, okay, take the whole square and then square root will give you what is going to be the magnitude of the shear stress. Okay. This is only the magnitude which we are calculating, okay, with respect to a coordinate system which we have defined x, y and z. Okay. We know the strain, the components of the strain along these directions, okay, both the pure tensile or compressive strain dilatation as well as the shear strain. Similarly, the stresses which are also there in these directions. What will be the response stress which is going to be generated because of the application of this strain, okay. So, the response stress depends upon the property of this material. The response stress in any particular direction in general will depend upon all the shear stresses which we are trying to apply, correct? The simplest way in which we can consider it is that, suppose I take a sample, okay, I try to elongate it in this direction. This will assume that the strain is going to be some epsilon xx in the x-axis direction, okay, or it can be taken to be z, because if we normally choose this as the z direction, if we choose this will generate a stress, okay. This we know that this stress sigma equals into, correct? But this strain generates a corresponding compression in the other two surfaces, correct? So, that is given by where nu is the Poisson's ratio, correct? Now, this can be written in terms of, that is, we find that the sigma yy and sigma z, sigma xx depends upon the stress which is there in the z direction, correct? That means that a stress in a particular direction depends upon, okay, the strain which is being applied in all other directions, it will have a component in that direction. Okay. So, if we write in terms of those components, then we will be getting a relationship between stress and strain in this form. Okay. What are these components? C11 is essentially that contribution to stress, okay, from strain which is being applied in the x direction, okay. This is from strain which is being applied in the y direction, right. This is the strain which is being applied in the z direction. These are all the contributions from the three shear strains which are being applied, okay. This is going to be the total value, correct? This is correct? So, now if we look, we have essentially 6 stresses, okay, and there are 6 strains are there, components of the strain, and the stress is also a tensor of second rank, and strain is also a tensor of second rank. Okay. When the relationship between them, when we try to write them, okay, in a matrix notation, essentially there should be, in general case we have 9 components of stress, okay. So 9 by 1 matrix, and here another 9 by 1 matrix. In an equation form, if we write it, each equation will have 9 terms. So essentially this will be a 9 by 9 matrix which will be required. The components of the property will be there. This 9 by 9 means 81 components are going to be there. When these stress and strains, okay, and they are infinitesimal and the body is in static equilibrium, we have derived earlier that in a symmetric case it will be only 6 components. Then this reduces to a 6 by 6 matrix, so 36 components which has to be there. Correct? These are all the, this is the equation which gives the relationship between stress and strain, which we call it as the generalized Hooke's law. Okay. So if you look here, there are 36 components are going to be there. How does it change to 21? If they have to change it to 21, there should be some components, okay, which should be equal. Okay. How does that happen? Okay. Before we go into it, now what we have got it is that we have got an expression which tells the relationship between stress and strain. Okay. So how to relate them? This expression we have. Okay. And we know the stresses which is being applied under different directions. Okay. And you know the corresponding strains also. If you know the stress and strain, we can calculate what is going to be the total energy, increase in energy of the system because of the application of the stress and strain, correct? So the total energy will be given by a formula of these type. Y plus sigma Z Z. Epsilon YZ sigma XZ into epsilon XZ plus sigma XY into epsilon XY. Okay. This gives nothing but the total energy which the system is feeling, correct? Is it right? Okay. This way, this expression is given in terms of stress as well as strain. Okay. We can write stress in terms of strain, so that this expression will become only in terms of stress, strain. We can write strain in terms of stress, then this expression can be written in terms of only stress, or this itself can be finally substituting for strain in terms of displacements, because the strain we define with respect to displacement of the atom from the lattice, the normal position. That way we can write this in terms of nothing but the displacements itself. Okay. So all the 3 forms it could be done. I would expect all of you to work out these formulations, okay, derive the expression for energy in terms of stress alone, strain alone, as well as displacements. Okay. That will give you a fair idea of what sort of relationship which exists between them. Okay. And another important aspect which we have to consider is that suppose I am deforming a sample. Okay. I first deform it in an x direction, okay, and then I deform in the y direction afterwards. So some energy is spent in deforming in x direction. It is being held in that. Then I try to deform in that x direction. The total energy is path independent. That means that suppose I deform now, instead of doing it deform first in the x direction, I give a deformation in the y direction first, okay. That is, suppose with respect to this coordinate system x, y and z, I deform the sample initially in the x direction and holding it at this position when it is elongated, deform it in the y direction, okay. Or I can deform it initially from this position in the y direction, the same amount of deformation, hold it and deform it in the x direction. The total energy remains the same, correct? So, if we apply this principle, okay, then we will see that, okay, the terms like Cij will be equal to Cji. This is what it will turn out to be, okay. Yeah.
No matter in which order we are doing.
Yeah, that doesn't matter because that energy is going to be that same. So this we can take an example also. Suppose we deform it in that x direction a little bit. How will we calculate that energy? That is integral 0 to some value, okay, epsilon x, okay. What is the stress which is going to be applied in this direction xx into d epsilon xx, correct? This will be half into sigma xx into epsilon xx, correct? And this we can write it in terms of sigma xx will be what? C11, okay, epsilon xx squared. Because when we deform in this direction, apply this strain, we make an assumption that there is no strain which is being applied in any other direction. That means all other strain terms are going to be 0, okay. That means that in this expression, if we look at it, if we see in this expression, only this term is going to be there, all other strain terms are going to be 0. That is why we can substitute this expression. Okay. Similarly, if we now keep it in this position, okay, and we apply the next strain, okay, then what it will happen? This will be from 0 to epsilon y, right, sigma yy into d epsilon yy, correct? This what it will turn out to be? This, if you look at this expression, okay, now it has xx already has been applied, so and y is also going to be there. So now sigma yy becomes, okay, C21 into epsilon xx plus C2 into epsilon yy. So this we have to substitute it now into this term and then do the integration, okay. If you do this, the answer will be x into epsilon xx into epsilon yy. There will be a cross term will come. This is how this energy term will turn out to be, okay. If you do it the other way around, okay, this is the total energy W. If you follow the path from 2, first applied in the y direction, elongation, then in the x direction, then this will turn out to be half into Cyy plus Cxy into epsilon xx epsilon yy. This is how it will turn out to be. Correct? That means that if the energy has to be that same, okay, this part also has to be there. That means that Cyx should be equal to Cxy. Okay. This is what it reduces now. The number of components to 21 components will be there. Okay. In this one, the terminologies which we have used it, C11, it actually means that it is essentially Cxx, then xx, this is for equal to C11. Okay. Suppose we use C12, this will be Cxx yy. This is how, okay. These definitions are already given in this table, okay. In this slide it is being given. One can go through this and get oneself familiarized with it, okay. Is it clear? Okay. But so far we talked about stresses which we consider as uniform throughout the sample, okay. But that need not be the case always. Okay. Yeah, before we come into this, let us look at one more aspect of it, is that the elastic constants now, the number of independent constants reduces to 21. Okay. So that means that if we consider a case like triclinic, where there is no symmetry which is associated with it, then the number of independent components of the stiffness coefficients which will be there is 21. Okay. Now, crystal systems, other crystals, a monoclinic crystal system if you consider, around one axis we have a twofold rotation is going to be there. What does essentially the twofold rotation means? That if we rotate the crystal around that axis, take it, the stress and strain values will be that same. That means that the property which relates that in those direction also has to be that same. So applying this norm, we can find out in which directions the property is going to be same, okay, and which are the directions in which the sum of the components, okay, the property may turn out to be zero values, sum of the components. Okay. That is, it will turn out to be, when we apply the symmetric rotation, some for some directions the permutation combination, when we take it, it will be a product of plus and minus. In some of them, that wherever that product turns out to be positive, okay, like what we did it for electric field vector and current density vector, to determine the conductivity tensor. I explained how it should be done to find out how many independent components will be there. Exactly the same logic has to be applied here. Then we will find out that some of these components, CHs, will turn out to be 0, okay. And because of that, for the monoclinic system, we will have only 13 independent components will be there, okay. This one can do it for other crystal systems also, taking the symmetry elements which are associated with it and find out how many independent components are going to be there. Finally, most of the crystal systems which we use are in the case of cubic system, where it turns out to be that we require essentially 3 independents, that is C11, C12 and C44. These are all the only components of the stiffness coefficient matrix which will remain.
If there is more symmetry, then less number of.
Yeah, the more symmetry, that symmetry element, the number of independent components will get reduced, because in those directions, because of the symmetry, they have to be the same. So the number of independent components get reduced. In some other directions, this symmetry consideration says that the value has to be 0. That's what it will turn out to be. So that decides the number of components. Some components become 0, some components only remain. This aspect of it, I will talk about the symmetry and the number of components and the crystal system separately. Okay. So essentially, one should understand that depending upon the symmetry associated with the crystal structure, okay, for the stiffness coefficients property tensor, when we consider it, which is a tensor of fourth order tensor or fourth rank tensor, okay, the number of independent components will change. For a triclinic system, we will have 21 components. Monoclinic, it is come down to 13. And finally, to cubic, it turns out to be there are only 3 independent components which are required. Okay. I think one has to remember only this much at this stage. So for a cubic, 3 components are going to be there. If the crystal is isotropic properties it exhibit, then the number of components reduces to only 2. Okay. So essentially it will be C11, C12, C44. Okay. And in an isotropic case, C44 becomes C11 minus C12. On this basis, okay, for an isotropic case, we can find out the relationship between stress and strain using generalized Hooke's law. So if you try to represent them, this is the form in which the expressions turn out to be. Okay. And now we can see that the sigma yz is given by 2 mu. Mu is the shear modulus. Okay. Twice mu it will come. Okay. Because epsilon yz is giving nothing but the shear tensor. Actual shear stress is going to be twice that of. That is why this 2 comes in the picture. Okay. And the lambda is called as a Lamé constant. Okay. Essentially, from these expressions, we have a lot of expressions which can be derived. One is between shear modulus and the Young's modulus. Okay. So shear modulus equals, because there are 2 ways in which shear modulus is being represented, using letter G in many books. Some books you will find that they use the term mu to represent the shear modulus. Okay. I had given both the expressions here. Okay. So G equals mu E by 2 into 1 plus nu, which is being given, correct? What is nu? Nu is nothing but the Poisson's ratio. This expression itself tells you what is the value of the Poisson's ratio which one can have. That is, suppose this nu becomes equal to minus 1. This term will become 0, right? What becomes into shear modulus? Infinity. Okay, that doesn't happen. So upper limit is 1 minus 1. Similarly, and another expression which can be derived is between E, okay, that is Young's modulus, this is the bulk modulus, okay, 1 minus 2 nu. From this expression, if we see, if nu equals half, okay, the Young's modulus will turn out to be 0, not possible. So the value of nu has to be between -1 and half, correct? This is the maximum value nu can have. Physical meaning of nu is that if we apply any strain to the sample, okay, in any particular direction, when we apply elastic strain, okay, there is going to be some component of that strain which it is going to introduce in the other directions. That is nothing but the ratio of the strain which you have applied in the longitudinal direction to the ratio of the strain which is being applied in. That is, if you try to a lattice which consists of atoms which are going to be there in different directions, which are all in equilibrium in 3 dimension. If I try to pull in one direction stress, what is it going to be its effect on the other directions in the how far it is going to be disturbed from the equilibrium position?
If we try to elongate one
Yeah.
material,
Yeah.
there will be limit up to which we can elongate.
Yeah, no, when we try to elongate it, it is being pulled away from the equilibrium position. Normally when we try to draw potential, okay, or energy versus distance between atoms, we are essentially drawing a graph like this. This is a non-dimensional plot. Now you look at a 3-dimensional plot, okay, that will have an effect on the crystal structure also into this. Okay. Now this, if you try to do any separation in one direction, in the other directions also which is going to be there, how far it is going to be affected, how far the bonding is going, that means bonding is going to be changed. Okay. If we take the second derivative of this bonding, this is going to give you essentially the stiffness constants, what it is going to be, okay, and how much it is going to be affected in terms of just the contraction. That is what the nu represents. Nu represents nothing but equals, suppose it is the epsilon yy by epsilon x. That is, if it is that x direction we are trying to explain, expand that sample, okay, what is going to be the corresponding contraction? That ratio is what we are defining it as nu. That is, E itself could be represented in terms of lambda and mu, and how lambda is defined in terms of mu and nu, okay. All types of expressions are there, okay. What are the basic loading geometries in which we can load the sample? Either in tension we can load by applying tension in one direction, or we can apply a hydrostatic pressure and load the sample, or we can apply just shear and do it, or we can have a balanced strain, okay. That is, we can have a shear by applying a balanced compression and tension. That is what we showed in the last class, okay, when we discussed about the how we can do a diagonalization. If a pure shear strain is being applied, how that can be converted into principal strains along axes which are inclined with respect to it. So far we considered that the stress which is being applied is uniform throughout the sample, homogeneous stress. But that is not always the case. Stress can vary, but it does not vary independently because some forces which are acting, okay. Here what we are trying to do, an assumption is that what is the rate at which the stress varies depends upon the position. That is, we can take a derivative of it and find out how much is the variation per unit length, okay. That is how it is being defined. So in this, what is essentially is being done, okay. The origin is at the center of this cube, okay. If sigma xx is the stress in the x direction, positive x direction, okay, then on this surface, okay, it is going to be half into, and the dimensions of this cube is delta x, delta y and delta z. in x, y and z direction. Then this is equal to half into delta x into dou sigma xx by dou xx, correct? Similarly, on this one it is going to be a negative value, that is sigma xx is one which is going to be there, and the negative direction it will be minus of it. Similar to that, we can write it for the shear strains as well. Okay, that is what essentially is being done in this diagram. So if we have got these values in any particular direction, what is it going to be? The force which is going to act, because finally the force balance equation we have to look at it. Okay, in this x direction, this difference, this one will give you the what is the force going to be there, normal force which is going to act in this interface, right? What is the area of this surface which is going to be there? Okay, is equal to this into delta y into delta z is the area over which it is acting, right? Because this is the x direction, okay, this is y and this is z. So this stress is going to act on an area which is delta y into delta z. So that is what it is being done. If we take the difference, we will be getting the force which is going to act on the x direction, okay, from that is component of the force acting in the x direction from the normal stress. Similarly, shear stresses are also going to act. Okay, the shear stress is on this y surface. If you consider it, we have a stress which is going to act in this direction, right? Similarly, this is the stress which is going to act in this particular direction. So the net, there is going to be a force which is going to act on this y surface, okay, but in the x direction. Similarly, on the z surface, okay, also on the x direction, there is going to be a net force which is going to act. Okay. The sum total will give you the total force which is going to act, correct? This is being given by this expression. So the total force which is acting in the x direction correct? Delta Z is the volume of this cube which we have considered. This is equal to, okay, force which is acting on that surface in the x direction, correct? And if we divide it by that volume, that tells you what is the force. Force, how do we represent it? Now, that means that suppose this force is acting on a sample, net force is existing. Then how can we describe a force? By Newton's law, we can describe this as this force is equal to mass into acceleration, okay? And if per unit density, if you wanted to find out, we can write this in terms of that unit volume. Then this will be rho into A, correct? So here it will be total force per, when we divide it force per unit volume, it becomes, so this will become rho into, in the x direction, d squared u by, if the displacement is u, that is this force acting gives out a displacement of u, then we can find out what is the force. Write this expression in terms of rho into d squared u by dt squared, and this term will disappear. So now this is what an expression which we get it, correct? This is nothing but a force balance equation. That is displacement in the rate of change of displacement in the x direction depends upon the rate of change of stress, okay, in the x direction. Suppose, because we are considering a Cartesian coordinates, now the displacement in x direction we have got a formula. Similarly, we can write an expression for displacement in the y direction. Displacement in the z direction, we can have a formula, right? So this is most important formula. This is a force balance equation. What it will turn out to be is that we know that sigma xx can be written in terms of sigma xx can be written finally in terms of strain, and the strain can be written in terms of displacement. So finally, this equation will actually turn out to be equal to u. This is how it will turn out to be. What is this equation? This is nothing but a wave equation. Okay. So the solution to this equation, okay, this is for sound wave propagation. Okay. So all the stress strain calculations within the body, okay, can be done by first finding out what is the displacement which is taking place, okay, because of some defect which has been introduced into the sample, okay. Then whatever is the displacement which we get it should satisfy this equation, that find it the formula for displacement in terms of x and y, okay, satisfying this equation. Then from that expression we can find out, that is, it will be essentially nothing but u will be a equals a function of x, y and z. Similarly, v okay. Once this expression has got it, we differentiate it, we get the strain, okay. Then if we using the generalized Hooke's law, we can find out the stress. So about the stress and strain distribution in the sample, everything, all the stress and strains could be calculated at every point, and the displacement should satisfy this wave equation. This is the most fundamental about calculating stress and strains in the material. Okay. If one understands this, then the rest of the job of finding out interaction between dislocations, the stresses and strains around dislocations, about various types of defects, it can easily be calculated. I have given this expression only in terms of stresses, but I would expect all of you to derive it in terms of, okay, displacement, which is the most fundamental equation. So we have considered whatever the essential important things, that is the different components of the stress. Using this relationship between stress and strain, okay, we can calculate the energy. That's if you try to deform a sample, okay, how what is the relationship between the relationship of energy with respect to stress and strain, okay, and from that we got information about how the number of independent components reduces from 36 to 21, okay, and then the force balance equation which we considered, and this is the one which is most important. In this expression, what is essentially important is that suppose the body is in a static equilibrium, nothing is moving, then the left hand side will become 0, then del squared u will become 0. That becomes the expression which one has to use it. Okay. So we will stop it here. Now whatever is the basic mathematics which is required for deriving stress and strain field around dislocations, around defects and energy of defects, that part of it we have completed. Okay. Now we will from the next class onwards, we will start talking about, because so far we have not considered about the point defect we have considered, About the line defects we have not started. We will have the class on line defects. Okay. We will stop here now.